Hello, everybody. So, in the last class, we left off talking about different types of coding processes. And we spent a little bit of time on them because I imagine that most of them, these vapor deposition tools that people use to coat various kinds of films, are new to you. And today, we're going to briefly go through a bunch of liquid deposition tools for coating with liquids. And we're going to talk about um, the specific application of paint, which is one type of liquid-based coating that you're all probably familiar with to some extent. So I have some illustrations or some examples here of things you may or may not be familiar with. But the most obvious one that I imagine that you've all seen before is painting. You know, you can apply paint with a paintbrush or some other kind of applicator manually, or this can be automated sometimes. There's also techniques like airbrushing, which produces an aerosol of particles, liquid particles that can coat a surface. Typically, you can get more precision in terms of coating thickness with that application. At the bottom, that's an image of screen printing. You can buy kits for that. This is how people apply patterns to T-shirts. It's also used industrially for labeling things, all sorts of applications there. So a couple of ones, if you look in the bottom, middle, and right, there are a couple ones that you might be less familiar with, and these are used oftentimes for coating polymers. If you want to make a polymer film on something, the middle bottom is an image of slot illustration of a technique called slot die coating, and this is a technique where you can put in a solution of polymer into thin and pump it into like a thin orifice. This sort of dye that's shown where the fluid is going into and coating on the surface can either stay stationary, or it can move, or the substrate can move, as illustrated here. And the dye can either be like a point, or it can be a sort of slot or a long shape, and you can make a film by either moving the dye back and forth across the substrate, or you can, or by moving the substrate around to coat it. So again, this is a very popular technique. This is something that's available widely industrially. So this was developed a long time ago, I believe, for film applications. So maybe when you all were very, very young, maybe you used to, before there were digital cameras, you had to send film over to Kodak and they mail you back pictures, like photos. Um, you know, back when we had like cameras that couldn't connect to computers. Um, maybe. Anyways, so this was a technique that Kodak and other companies would use to make their films, which they had on giant rolls, and that was consisted of many layers of polymers that had different photosensitivity, and that would result in color when being exposed. So that was a big engineering challenge, and that was a combination of chemical engineering and also optical engineering by a bunch of chemists, engineers, physicists working on this together. So the other one I have here on the far right is doctor blading. So basically you take a blade of some sort, and you can have some polymer that feeds through in the liquid form. And you use the fact that you're making there's a small gap between this blade and a film, and whatever substrate. In this case, we have a reel of some kind of plastic sheet or something like that. And you can apply a coating very uniformly like that from this, and you make it into you roll it up in the end, as you can see in the bottom. So again, that's a very common technique also. I believe that was developed in the early days of film processing, where they're making these giant rolls of film that they end up cutting up and then serving as what you'd use as photographs of stuff. Okay. So again, I just wanted to go through some of these briefly. Some of these you're familiar with, some of them you're less familiar with. The other one that is complicated to explain, but I will post a video of, is printing, specifically inkjet and laser printing. Laser printing is not a liquid-based, it's a solid-based aerosol of particles that happens there. But inkjet printing is liquid-based, and it's actually a very fascinating technique if you if you look at what's actually happening, there's very fast stuff happening in each of those processes, and more than you would expect. So I will post some videos related to that so you can get some background on that. But it certainly incorporates colloid chemistry as well as a lot of engineering. So I'll do that. So we're going to talk about paint now as a specific application of coding, and talk about the chemistry of paint and what's in there, stuff like that. Okay, so you all may be aware as engineers, a lot of chemical engineers as well as mechanical engineers work in the area of paints. So many companies like Sherwin-Williams, for example, is a large employer of chemical engineers. Also, companies like Dow Chemical, 3M, et cetera, they make components that go into paint. It's a big industry. You can imagine that for even like commercial, residential purposes, there's lots and lots of paint sold every year. So very, very tiny savings in cost can affect the bottom line a lot, just because of how much volume of paint is sold in a given year. So usually what companies are looking for are marginal, very small improvements to cost when they're making these, and also trying to accommodate regulations and things like that. So it's an interesting engineering challenge. So let's talk about the components of paint. What is paint made out of? So we're going to classify this as a few different things, using a few different words, and I'll explain what they are in a minute. So we'll have something, and I'm going to use the industrial terminology here. I'll explain what they are. So we'll have something called a vehicle, a pigment, which you can probably imagine what that is. Filler. And the last thing we'll mention are generally additives, which again should be somewhat self-explanatory, but let's talk about these briefly. So the vehicle is going to be comprised of a solvent that carries everything that's in the paint, plus binding agents. So we'll call them a binder. Right? Solvent, again, is whatever liquid that is suspending everything that's in your paint. So that can be water-based, it can be what we call oil-based, or typically when we say oil, that's some organic solvent there. So the binder, though, is something that's more complicated. So with paint, paint differs from a stain. So if you have a piece of wood, you can apply different types of finishes to it. One would be a stain, which can add color, for example, to a piece of wood. And paint is a coating that has other aspects than just color. So the binder provides different properties, such as toughness, flexibility, and durability. So this binder is typically classified into two different components. We usually talk about oil-based paint and latex paint. And the oil is a bit of a misnomer, but not exactly. Has a historical purpose. So latex, you may all be familiar with. To some extent, that's rubber, or what rubber originates from. So historically, people would take natural latex. That's what is supplied if you go to a rubber tree. So there's a thing called, for those of you who may not know, there's a thing called a rubber tree. So it grows in tropical areas. You can like cut a slice into a rubber tree and tap it. Latex, like this whitish liquid, will pour out of it. You can collect it at the bottom. People do this manually. They still do it nowadays, and that's where natural rubber comes from. There are synthetic rubbers. Those are made out of various polymers like styrene butadiene and other things like that. So oftentimes these are interchangeable depending on application. For more high-end applications, oftentimes the synthetic rubbers are used. For lower cost applications, sometimes latex is used, or natural latex is used. So latex now has grown to any type of rubber particles that are dispersed in a solvent, whether they're synthetic or natural. So latex has a broad definition, but it originates from that natural rubber source, which is this natural latex, which is this milky liquid that you get from a rubber tree, which happens to be colloidal particles of natural rubber. Okay, so oil originates from old paint technologies. So back in the day, people used to use linseed oil. So linseed is another name for flax. So as a dietary thing, we call it flax. Industrially, we call it linseed. So linseed oil polymerizes easily upon exposure to oxygen. So it's a liquid material. It's a liquid, and it will oxidize. You can still go and buy, if you go to the hardware store, you can buy linseed oil. You'll see oftentimes they call it boiled linseed oil, which is a way that they partially oxidize it to start with, so it will dry faster. So this is still a thing that you can buy. It's expensive nowadays, and it's been replaced with artificial or synthetic polymers for the most part, which are cheaper and do much of the same job, although they actually tend to be less durable than linseed oil, but they look better. They form better coatings too. They're more aesthetically pleasing, the artificial ones. Okay, so that explains what the binder is, and solvent is another challenge right now. As engineers, there are a lot of drives for moving away from volatile organic compounds. So, when I first moved here to Ames, it was the first time I ever bought a house, and I moved into this brand new house, and it smelled like paint, and it smelled like paint for like 3 years. Every time I left, on a conference or something, like I come back home, it smells like paint. And, I got sick of it. I moved out of that house. That was because the builders who were building that house, are using cheapest paint they could find, and it was leaching paint fumes out for years and years and years. So, my sister actually is a chemical engineer, and she works for Valspar, a paint company. So I asked her for a recommendation when I moved to a new house in Old Town. So I live in a very old house now. What paint should I use? And she recommended a paint that has no volatile organic compounds. And after a day, actually, that paint smell was gone. So this is becoming like an increasing concern. There's more and more regulations that are in place. And also from the consumer side, people don't want their house to smell like paint all the time. So anyways, that's an engineering challenge, because usually people use those volatile organic compounds because they're really good solvents. They do a really good job of doing the job of what we want it to do, to disperse stuff well. But there's bad sides to it. And the non-volatile, the VOC-free paints have the other disadvantages. For example, they stay tacky for a while. I have little kids at home. That was one thing I was worried about, that we can't touch the wall for a week, right? So I needed to physically restrain my children quite often to prevent them from touching the wall for a week, which, let me tell you, was a near miracle that we got it to work. But yeah, I basically made them stay outside almost all day for a week. So anyways, pigment. So pigment has two components. But generally, so let me spread this out a little bit so we have space here. Okay, so pigment. So pigment is typically made out of some kind of granular solid. So granular meaning it's particulate, dispersed in paint. And it has two different functions. There's two different types of pigments. It can provide color or opacity. So opacity is the condition of being opaque or not being able to see through something, right? So if something is opaque, you cannot see through it. So typically, paints are not see-through, right? You want, in fact, to one engineering challenge is that this opacity pigment that is added to paint is the most expensive part of the pigment. Typically, this is made out of titanium dioxide, which is white particulate material. It's a mineral that you can extract from the earth. And it's the most expensive part of paint. So we want to have two functions with paint. We want from the consumer point of view, we want them to be able to have minimal effort, meaning they apply one coat of paint and you can't see through any of what you just painted, right? On the other end, we want to, so the TiO2 is what does that. On the other end, TiO2 is the most expensive thing. Titanium dioxide is the most expensive thing that we put in paint. So we want to minimize how much titanium dioxide is in the paint. So this makes an interesting challenge in terms of optimizing stuff. So a lot of the engineering challenge actually combines developing new chemistry to optimally disperse the TiO2 particles, combined with optical physics to maximize the scattering effects that we have from TiO2. TiO2, just like we talked about light scattering before, the purpose of TiO2, it's white, but it scatters light, so it's able to reflect and diffract light in different directions, so it does not simply pass through because it has a very high refractive index. So how do we disperse these TiO2 particles optimally so we can minimize the amount of TiO2 while maximizing the scattering effect? So actually recently, or maybe 3 years ago, we had a seminar speaker for graduate students. We have a weekly seminar speaker, and the seminar speaker was a scientist. Now he's actually a professor at UMass Amherst, but he was a scientist, then research engineer at Dow Chemical. And this was his area of research, especially trying to optimize this problem. So he's actually a chemical engineer. He's in the National Academy of Engineering. So he's a very well known person, and he made his career just off of this, solving this problem industrially. Anyways, so this idea of, so this color aspect are either some kind of mineral or organic compound. That can be different things. Back in olden days, these used to be things like lead and cadmium because they have pretty colors, like different oxides of those materials. But we know now that they're super toxic, so we don't use them anymore. So like you'll see even now, you will see labels of colors, something like cadmium red, right? And that's some kind of cadmium compound, like cadmium oxide or cadmium selenide or something like that, or some combination of that, that has a very bright, vibrant red color. It serves very well as a pigment because it refracts really well, but it's toxic. Likewise, lead is a very good paint material, lead oxide, but starting in the 1970s, that's been banned in the US and most countries because it makes people less smart quantitatively. It lowers people's IQ. So there's a whole if you ever think your parents are too bright, their entire generation has half of one standard deviation lower IQ than the generation before them and after them. So that thanks to lead paint and lead in gasoline, which is also taken out. So you can tell them that. I tell my parents that all the time. So anyways, but yeah, that's a real hazardous thing. And even in my house, like I live in a 90-year-old house, we have our children tested every year for lead because there is areas where paint peels, and my kids are outside all the time. I wouldn't be surprised if they eat stuff like dirt. I know that happens. So it is a really big problem. And in fact, my youngest child did test high for lead at one point. So we needed to do some intervention there to make sure that it wasn't becoming a bigger problem. So yeah, So it's a very actually interesting social economic thing. People have sort of looked at the long-term economic impact, like this has increased things like crime and other aspects. This can all be attributed to lead paint. Yeah, so big problem. Okay, so this ability to have opacity, so this thing is called hiding in industry. Just like the word hide. So the idea is when you make a coating, you want to hide whatever is behind it, right? So they quantify this into a property that we call hiding. So this TiO2 is called a hiding pigment, right? So it's not for the purpose of color, it's for the purpose of hiding whatever is behind it. So TiO2 is the most commonly used thing because the combination of cost versus even though it is expensive, the combination of cost versus quality is right. Okay, so filler. Filler is exactly what you might expect of it. It is like additional cheap stuff that you put in to paint. Additional, usually inexpensive material. So it can have a few functions. It can increase viscosity in some cases. The other thing that it can do is provide volume just to make your whatever film you make thicker. So it has more thickness to it. So it doesn't have to have any particular great properties other than it takes up space mostly, and it can have some rheological properties. So examples of this are things like clay or talc. So again, things we can get from the earth that are relatively cheap that we can mine in sort of kiloton quantities in relatively high purity and just pulverize and stick in there and disperse them pretty well. So these are relatively inert substances. They don't interact with much of anything. Clay, it turns out, is has surface charges, so getting those to disperse can be challenging if you're in a non-polar medium. So oftentimes you'll have to use surfactants to ionic surfactants to bind to the surface of these and disperse them. So anyways, let's talk about additives. That gets into our next thing. So this has a lot of functions. So these modify different properties. So typically chemical, thermal properties. Can we have other types of additives too? Could be flow properties, for example. Yeah, I'll put that. So like rheological properties. So typical components here are things like antimicrobial agents. That's another. Let's see, what else we got? Antifreeze. Surfactants. So we use surfactants to help stabilize and modify, to help stabilize a lot of the components. In some cases, surfactants, like I said, if they're charged, they can stick to charged species like talc or even TiO2. This person I told you about, John Clyer is his name, the professor, actually is the department chair now, UMass Amherst. He actually worked on different polymers that could attach to TiO2 that could provide enough steric hindrance to separate them apart so they don't aggregate, because that, from a molecular point of view, they found that to be the biggest way that they can get cost savings from paint is to be able to formulate it differently such that these TiO2 particles would not aggregate and stay a certain distance away from each other. So surfactants and other types of polymer additives can contribute to that. So I think that gives you an idea of what is in paint. What I want to talk about now is more of what are challenges? Like why is applying a coating like paint hard? You know, what challenges do we need to overcome from a physical level? We talked a little bit about this very briefly before, but let's go into this in a bit more detail. Liquid coatings. So again, in the case of paint, we're applying a liquid coating. We want it to dry to a solid. But let's talk about what are the problems here. Okay. So one thing that I talked about before, let me show you a picture, is this effect here. So this is coffee. So this is called the coffee ring effect. Okay, so if you have a droplet of liquid or any kind of liquid, you'll see that as it dries, so you initially have some liquid, it's sort of uniform. As it dries, you'll see that everything tends to move towards the edges. So why does this happen? Right, so that's one type of problem. I think I have one more thing that I want to show you if I can find it. I can see this. Maybe I don't have another example here. Okay. So before we talked about this marangoni effect. Right, we apply that to bubbles. Right, so the principle of this marangoni effect is that a surface tension gradient causes flow. Right, so if you have a higher surface tension at any point, there will be flow from low surface tension to high surface tension. So we use that phenomena to explain the stability of soap films that you would use to make bubbles. And that would apply to even bubbles themselves. If you made a soap bubble, why you're able to touch that, for example, without it bursting instantaneously, or why it's even stable to begin with. So in this case, this is a slightly different variation. So let's draw a cross section of this coffee drop. Let's see, do I have brown here? No. So that's our coffee. Okay, so we spilled our coffee on our desk or something. I'm sure I have one of those droplets somewhere around here. So it starts evaporating, right? We have some non 100% relative humidity condition. So it will begin to evaporate. Okay, so if we look at this interface here, so right at the edge, this is going to have a slightly higher surface area where it's in contact, near where it's in contact, because if it's spreading out. Or surface area to volume ratio. It's not slightly higher, it's much higher. So what happens here is the edge evaporates a little bit faster, right? You can see this, right? That's why oftentimes you'll see things evaporate from the edge in. So in turn, because it evaporates slightly faster, it becomes cooler, right? So if you remember the dependence of surface tension on temperature, surface tension goes up as T goes down. So what we say here is that we'll have a slightly higher surface tension than, say, here. And we'll have, this will result in convection toward, or not convection. That's the wrong word here because not exactly convection. It's called flow that's driven by the surface tension toward edge. Okay, so that's one technique or one problem that we face. The other one I'll probably show you in a video. It's a bit more complicated, although maybe I can draw an example. How much time do I have? It is 11:43. Yeah, I will pull up my notes. So there's another thing that people know well, which is called a Bernard-Marangoni convection. So suppose you have some pool of liquid that has some thickness d. So again, we talked about the idea of surface tension having a temperature dependence. We can write a simple model for that. We can say the surface tension as a function of temperature would be some surface tension at some standard state minus some parameter, let's call it gamma, it's just a constant, times the difference between the actual temperature and that reference temperature. Okay, so this is just a linear model. We're saying that the surface tension will scale linearly with temperature, right? Where maybe our gamma 0 is, say, at 25 degrees Celsius. So what we would see if we were to monitor, let me blow up on this a little bit to make this a little clearer. Suppose that this temperature here, let's say that this is hot, and up here it's cold. So this heat difference can be natural. It could be just because you have evaporation occurring at the top surface, which is causing it to cool slightly, or it can be because you're actually applying heat to the bottom. You can observe this effect that I'm about to show you in either case. Okay, so what would you see if you were to monitor like a one particle, you know, one let's call it a discrete or a differential unit of water, right? It's at a hot place and it's cold above, right? We know from mass transport or heat transfer that we will have some rise here. So it'll go up, right? And as it approaches the surface, it will need to move in one direction or another, right? So it's either going to go this way or this way, right? Because there's going to be one behind it also that's moving, and it's going to force it to move out of the way, one direction or another, okay? So what will end up happening is you'll get some vortices that occur. So you'll get net fluid movement around in a circle like this. Likewise, you'll have one that's moving in the opposite direction like this. And you'll see that you'll have these sort of opposite direction vortices. So here we have this moving down. You have next to it one moving up, down, up, etc., like that. Okay, so that is convection, right? We all know convection. So this is what happens. You can imagine this happening. So like in words, we can call this our blob of water. We can say that water blob moves towards surface. It'll lose heat as it rises, right, to the environment. And then the blob diverges, right? If it's a infinitesimal blob, it'll go one way or another. If it's an actual packet, you can imagine it splitting up. There's a couple ways to model this. Okay, so let's look at this surface again. So we have these sort of convection cells that we're saying occur. Actually, these should be in the same direction. Sorry about that. This is going up, right? So these will be, the neighboring ones will be in the same direction. Sorry about that, that's wrong. Okay, so we can get these convection cells happening. You can show this using sort of particle tracing experiments. You can put particles in water that are inert, and you can watch these particles move around. But there's some more interesting stuff that happens that you can see under certain conditions that happens even without particles. So again, we have these convection cells that form. And because we have the hot water rising up in this direction, this will be warm. And as it moves away, it'll be cool. And over here, yeah, it'll be cool, let's say. And we know because of our relationship of surface tension with temperature, the warm place, the surface temperature will be a little bit smaller, and the cool places, it'll be a little bit larger. So this has an effect of driving flow, not just convection of that differential packet, but also bulk fluid flow. So what we would see happen is, let me draw my convection cells first. So let's draw 4 of them. Say up, up, down, down, up, down, down. So what we see is flow towards the cool sections, right, where the fluid is flowing down and away from where the fluid is flowing up, where it's warm. So fluid is flowing up, but that's warm and has lower surface tension. So we will have fluid go away from that. So you'll actually see the water surface change in its shape. Okay, so I'll show you a video of this actually happening. This is something that you can do at home if you set it up carefully with a frying pan full of oil. If you do this very carefully, it works better in a laboratory setting probably, but you can see this at home. Okay, so these are, you can model this a little bit using transport equations, right? Most of you or all of you have taken some form of transport phenomena, so I won't bore you with all the derivation. But you can calculate things like the time it would take for this packet to rise. And this would be related to the viscosity times the distance, the thickness here, times the change in surface tension that we see. Let's see how we're doing on time. We got some time. Okay, good. So there's also the time. So there's that rise time. There's also the competing process, which is just diffusion, right? So we have diffusion that could occur just to thermal diffusion, right? So there's also the diffusion time. So if it's diffusing away faster than it's rising, you wouldn't necessarily see this happen, right? This convection or this rise time needs to be fast compared to diffusion. And this you can calculate to be the square of the thickness over the kappa, which is the thermal diffusivity. So we can take the ratio of these. Tau rise over tau diffusion. And since we have a model for this delta, what do you call it? The delta gamma in terms of delta gamma in terms of capital gamma, you'll find that this ends up being that capital gamma parameter that we have in that model that we derived before for surface tension dependence of coefficient, surface tensions dependence on temperature, times the difference in temperature in the system times d over mu times the thermal diffusivity, right? So you'll notice that this is time over time. So this is a dimensionless group, right? So we found another dimensionless number to add to your big collection that you've collected over the years taking transport phenomena and reactions. Maybe you learn some more. So this is known as the Marangoni number. So this process, so you have a question in chat. Let me open that up. It's supposed to be tau rise over tau fall. or tau, this is the, yeah, it should be tau rise on, oh no, that doesn't look right, does it? Huh. Maybe maybe my notes are messed up. So yeah, that does look wrong, doesn't it? Yeah, it should be tau diffusion over tau rise, I think. Okay. So anyhow, what we would find, so this process where we get this happening, this effect, is called a marangoni instability. And it happens when the marangoni number is greater than some critical marangoni number of about 80. But let me double check this to make sure that I didn't mess up. I'll send a message after class. Okay. So this has other effects that you can see every day. So this last thing that we'll talk about before class ends is if any of you held a glass of like wine or other types of alcohol, you can see this phenomena happens in anything that's wine or higher proof. So whiskey would work if you have a glass of it. So if you have a glass of wine, you have this interface here where it forms a meniscus. So what we'd see here is we have a thin layer that forms here. So again, because of this thing, we get this evaporative cooling effect. And as a result, because surface tension goes up with temperature, we have lower surface tension and surface tension driven flow in that direction. So by the way, this was studied by Thomson in 1885. He published a paper on this back then. So what you'll see is you will have, if you were to observe this, so this is going to be my attempt to draw this. So what you'll see is you'll have liquid from this rise up to the top because of surface tension driven flow. Eventually the weight of gravity would catch up to it and you'll see it sort of pool up here and flow back down. And you see that all over. And you see these start to form bands. And these things dripping down, these bands would start to merge together a little bit and form bigger droplets. So these are often known as tears of wine. So it's a really well-studied phenomenon. For those of you who have alcohol at home, you can do this yourself. It doesn't take any effort. It happens spontaneously. If you have a relatively clean glass, it'll happen if you can just let it sit. If you don't drink alcohol, you can find a friend maybe who does, so you can observe it. But yeah, it is something that you can watch and you understand why it happens. People have studied this for a long time to figure out exactly why this happens. So it's this combination. These are effects of surface tension driven flows. Just to hold off Why am I talking about all this? These are things we want to avoid when we're trying to code stuff, right? This is what happens naturally, and we need to prevent these types of phenomena from happening. We don't want our fluid surface moving around. We want to stay in place and not form coffee rings, not move all over the place and flow up onto the sides of stuff. So as engineers, we can understand this is what nature tends to do. And these are the things that we want to avoid when we make a coating. So that's where we'll end off for today. There's a question about the final project. There's a weekly objective. So I'm going to have you turn in something. I'd like you to turn in something, but it's going to be just a checkpoint. So again, just like this week, for those of you who maybe needed some pushes in the right direction or didn't complete it exactly, the idea here is you turn in whatever progress you made, and I can give you feedback, right? So once you sort of are at the place where I expect you to be, I'll give you full credit. So yeah, there will be an announcement posted. The expectations will be basically building along what we've done last year. What I'll probably do is make it due on Monday, so you have the weekend to incorporate my feedback instead of Friday. So I'll post that there, and maybe well, there's a question about the expectations. I'll make sure that the general expectations are there too. So thanks for that question. I was planning on posting that to Canvas today. Okay, but other than that, I'll stick around if there are any other questions, and have a good day. I'll see you on Friday. Remember, there's no quiz. There'll be a take-home